Alright students, we're going to go over homework on page 40 and 43. On both pages it is 1 through 6. So looking at page 40, number 1. Heather and Matthew walk with an average velocity of 0.98 meters per second to the east. If it takes them 34 minutes to walk to the store, what is their displacement? So we're looking for displacement. So if we have our base equation, velocity equals displacement over time, we can then solve that for displacement by multiplying time over, and we're working with this equation here. If we put in our velocity as 0.98 meters per second and plug in our 34 minutes, we want to change that into seconds, and I could be off here, I think it's 2040, and you just multiply those two numbers, you should get an answer. I'm not going to tell you the answer, but you should be able to calculate that one out. Number 2, same sort of question. If Joe rides his bicycle for 15 minutes, there's your time, and with an average velocity of 12.5 kilometers per hour, there's your velocity. How far did he go? Now, if you don't change your units, you're going to get some weird conglomeration that has kilometers, hours, and minutes. In reality, we want to change the 15 minutes probably to a quarter of an hour and keep our units the same by doing so. Number 3, if it takes you 9.5 minutes to walk with an average velocity of 1.2 meters per second to the north from the bus stop, how far do you go? Again, we're given minutes and we're given meters per second. Change your minutes here into seconds and multiply again. For number 4, Simpson drives his car with an average velocity of 48 kilometers an hour to the east. How long will it take him to drive 144 kilometers on a straight highway? Well, here we are given displacement and velocity. We're solving for time. You just plug those in and, solve for t and get what you get. So plug your velocity here, plug your time, or plug your displacement there, get your time. I think it comes out to something like 3 hours. Then in number 5, take a look at the previous question. How long would it take Simpson, or how much time would Simpson save by increasing his velocity from the 48 in the previous question to 56 in this question? So you're going to take the distance from the displacement from the previous question and input that here. So we're still going to have 144 here, and we're going to put in the new 56 here and solve, and I think you get like 2.5 or something like that. And then you want to subtract the 2.5 hours from the original 3 hours, and you get an answer just shy of half an hour. For number 6, it's a two-part problem. We have a bus trip, and they travel, in the first leg of the trip, they travel 280 kilometers with an average speed of average velocity of 88 kilometers per hour. The bus stops for 24 minutes, and then it goes another 210 kilometers with an average velocity of 75 kilometers per hour. There's a 3-part trip and 2 parts of questions. Part 1, how long does the total trip take? Take the first leg of the trip, the 280 kilometers at 88 kilometers an hour, find the time. Take the third leg of the trip, 210 kilometers per hour for 210 kilometers at 75 kilometers per hour. Solve for time. So you'll have the first leg of the trip time, you'll have the stop, and then you'll have the third leg of the trip time. Make sure the units agree with each other and add those times up and you get A. For part B, what is the average velocity for the whole trip? So here we're going to find average velocity for the whole trip by taking the total distance or displacement for the whole trip and the total time for the whole trip. And that displacement and that time will give you the average velocity for the whole thing. Now on to page 43. Number 1, what is the shortest possible time in which a bacteria could go 8.4 centimeters across a petri dish if it has a speed of 3.5 millimeters per second? You've got a unit disagreement here. You need to change something in there. Perhaps it would be easiest to change your centimeters into millimeters, and then it's just like we've been doing, solve one of these 2 equations for time. Number 2, a child pushes a shopping cart at 1.5 meters per second. How long will it take to go 9.3 meters? Again, you've got x and v, find t. Number 3, though, makes you think a little. You got a person swimming laps. And in the lap pool, they're swimming along, and they swim, let's see, swims from the north end of the pool, of a 50-meter pool, in 20 seconds. North end of the south. I'm going the wrong. I want this one here. Goes from the north end of the pool to the south end of the pool, 50 meters in 20 seconds. The return trip, then they end up going back in 22 seconds. What is the average velocity for the first half of the swim? So we're going to take our 50 meters with our 20 seconds. Boom, no problem. What is the average velocity for the second half? Again, now I would call this a negative 50 meters because this was positive 50 going that way. I'm going to call this negative 50 going the opposite direction. And do that for 22 seconds. So distance and time there. Then for the third question, C, what is the average velocity for the whole thing? Well, if we started here and we ended here, our displacement might be 0, therefore our average velocity might actually be 0. 0 divided by 42 is 0. Number 4, two students walk the same direction on the same path, along a straight path with constant speeds, one at 0.9, one at 1.9, assuming they all start at the same point at the same time, how much sooner, so a difference in their times, will they reach the 780 meters? Do two calculations, 780 meters for both of them, use their individual velocities, find their individual times, and subtract. And you know what, skip over part B for right now. We'll go over that in class. That's a bit of work on that one. Number 5. Does knowing the distance between two objects give you enough information to locate them? No. Just because things are 10 meters apart doesn't tell you anything about what 10 meters are you talking about? Are they 10 meters apart in the classroom, 10 meters apart on the football field, 10 meters apart in the hallway? No, that's not enough. Number 6, looking at two graphs. And there's a bunch of questions about the two graphs. And all I'll tell you here is as the bear travels, the slope of the line represents the velocity of the bear. So in letter A, between 0 minutes and 15, he's moving pretty quick. He kind of slows down for 5 minutes, and then he has a pretty regular velocity from about 20 minutes till I think it's 40. Then at 40, his velocity becomes negative. He ends up going backwards in space for, what was that, about 10 minutes? And then he ends up going positive velocity again, forward. Bear B, on the other hand, is going forward the whole time, although between 20 and 25 minutes, he seems to have kind of stopped going forward. Okay, so those ideas right there will help you answer the questions for number 6.